Hi everybody. This is an overview of the Theory of Computation class. So at the high level, in this class, we're going to start with an introduction, which is what we're doing right now. And then we're going to move on to regular languages and finite automata. Then we're going to move on to context-free languages. Then we're going to study computability and Turing machines. And after all that, we are going to see complexity and the P versus NP question. It will be a long journey, and we're going to start right now. So this class really teaches you two things. The first thing is mathematical maturity. And the second is theory of computation. Mathematical maturity is the key to success in your scientific career. Okay? Everybody wants mathematical maturity when you interview for a position in a company, in industry, or in academia. They want candidates which are mathematically mature. And in this class, we're going to practice mathematical notation. So for example, sets, quantifiers, and so on. And we're going to get some exposure to proofs. Okay, so proofs will not be a major focus on this class, but we will see some proofs. We're going to get some exposure to proofs. And then, of course, we're also going to teach theory of computation. So what is theory of computation? We're going to develop models of computation and ask questions like, what can and cannot be computed in these models? And how quickly? And with how much memory? And so on. And these questions are really fundamental to all of science. More and more, the questions that are asked in science are questions about computation. Like even in biology, when you need to deal with an extremely large amount of data, you're faced with computational challenges. Can I process this data and compute certain statistics or some other properties? And so the questions become computational. And also, in physics and in economics, they need to simulate large-scale models and so on. And examples of computation can also be found in nature. Like there are experiments, that the birds can count up to a certain number and so on, that animals solve some hard problems. And the most famous open question in the field is the P versus NP question. And this is one of the 7 or so millennium problems, and each of them has a price of $1 million, which is really not that much, right? If you think of the magnitude of this question, probably you want to make this, maybe 1 billion or maybe 1 trillion. Okay, and you're going to learn what this question means in this class. So let's do now some overview of the material in theory of computation. We're going to see automata theory, then we're going to see computability theory, and then we will see complexity theory. So automata theory will start with the finite automata. So you can think of this as computers which have no memory, and they sound extremely restricted computers with no memory, and in a sense they are, but the restriction is also useful because we're going to be able to analyze them very well, and they have a strong motivation. For example, numbers, names, the syntax of the variable names and function names and so on in programming languages can be programmed typically with a finite automata. So for example, x equal to minus 0.0565, is a valid expression in many programming languages, and someone has to check that this thing is typed correctly. Like for example, I did not type something like 0.0 plus minus 5. Okay, this will not make any sense. Okay, and the thing that checking this is a finite automata. Then we're going to move on to context-free languages, context-free grammars, and here you can think of computers with a memory which is a stack. So it's not quite as general as modern computers, but it's not zero memory like before. It's a memory and it's a stack, so you can push and pull items in memory in a certain order. And the motivation here is that the syntax of programming languages, not of variable names and stuff, but the whole language, like the grammar of a programming language, constructs like if something happens, then something else then happens, is typically described by a context-free grammar. Like if you want to build a Java compiler, I did it once, and I borrowed a couple of books which were the entire context-free grammar of the Java programming language. Okay. So again, someone has to check that this if then else and other constructs like this are probably are correctly written, and the thing that does that is a context-free grammar. Then we're going to move to computability theory, and specifically we're going to look at the type of machines which are called Turing machines, because they were invented by Turing. And these are it's a model of computation that you can think that basically has unlimited computational power. So you can, in a sense, compute until the sun dies. Okay, you can compute it for an exceedingly long time, and there's a strong motivation for studying this model is the question of what problems can be solved at all, regardless of how much time and memory you're willing to throw at this problem. Are there problems that inherently take too long of a time for any Turing machine? Okay, and an important example is, given a program, does the program have a bug? Okay, and we're going to prove that this thing is impossible to solve, regardless of how much time you're willing to wait. There is no algorithm that solves that problem. There is no computer that can solve that problem, and we're going to prove this impossibility result in this class. Then we're going to move to complexity theory, okay? And here is where we get as close as we're going to get in this class to modeling your laptop, your desktop, okay? So the motivation here is what problems can be solved fast, okay? Not just can be solved at all with any amount of time, but when can they be solved fast? Okay, this is what we care about on a daily basis. I want my computer to run fast. And an important example of a problem is the SAT problem, in which you're given a formula with some number of variables. Think of like 1,000 or 1 million. The formula is built of variables and things like not, or, and you want to know if it's satisfiable or not. So if you can find an assignment for the variables that makes the formula true. And the question is, does it take 1,000 years or 1 second to know this? Can you do it extremely fast, or does it take a very long time? And this, perhaps surprisingly, is the P versus NP question, which I alluded to before, right? Whether you can solve this problem fast in time which scales only with the power of the length of the formula is the P versus NP question. So a recap of this material, we're going to see automata theory, in particular finite automata. Then we're going to see grammars, context-free grammars. We will see computability theory, Turing machines, and complexity theory. As we see from this outline, computation has many guises, okay? It can be an automata, something with no memory. It can be a grammar. It can be something which computes for an exceedingly long time. It can be a formula. Okay, all these things are aspects of computation. We're going to study them more. Okay, computation has many guises, and in a very strong sense, nature computes.